Hello. Right. I'm going to be doing a talk on whitewater streams. What whitewater streams are just streams, but fast streams, fast Node.js streams. Like this thing that's loading up any second. So, what are whitewater streams? So what are streams? So streams are pretty much used in every component in Node Core, from HTTP, HTTPS, .NET, FS, your process standard in, out, error, TLS, TTY, UDP, zlib, crypto, pretty much every module inside Node Core. So with that in mind, we've kind of, what do you use streams for? So one of the things that I use streams for is when I'm dealing with lots of data coming from a database or a flat file, transforming that data into something else and then outputting it somewhere, like in a nice format, probably like XML to CSV or something like that. So let's kind of like start off and look at this kind of example, dumping from a large data set, transforming the data and piping it to an output file. Let's pretend this database is just kind of a flat file, and just kind of like hook it all together, stream it through, benchmark it, see where the performance hits are, etc., etc. It's a duplex stream, which means it reads and writes itself. So you read from the DB, transform it, and then write to wherever you need to write it to. So you usually do that using kind of like a fs.create read stream, pipe that into your transform stream, and then do a fs.write stream and pipe that out somewhere. So in this case, we're kind of reading from a flat file, which is a genome sequence, which is just basically a large text file with kind of A to G letters and kind of formatted in a nice way. It's of a famed plant. It is, so to kind of benchmark this, we're going to do that kind of like read stream, transform stream, write stream. So one of the problems of kind of like benchmarking kind of our streams is that I/O is slow in comparison to kind of like dealing with stuff in memory. So if I was kind of like going to benchmark something, which is kind of I/O, read it from disk, do something, and then write to disk, you're going to be waiting for I/O most of the time, right? And if you're trying to make streams faster, like in core, or your actual processing faster, that's not going to happen. So how do you make it faster? So one thing is by removing all of the I/O and kind of like loading it all into memory and then just benchmarking that. And that's what I did. So let's have a little look here at oops. Oh, that's on the server. Wrong one. This one. Cool. Right. Can you all see that all right? Yeah. Yeah?
Can you zoom that?
Yeah? More? There we go. Large font. Is that right?
Yep.
There we go. So number 1.js. So let's look at 1.js. Oh, this is going to be difficult to view now. But anyway, let's get rid of that. There we go. So this is just pretty much reading a file into memory, putting it to JSON or kind of a JSON object in memory, and then we're going to create a kind of a buffer here and just a test function to do our stuff. So we're just basically creating our own readable stream. So we're going to be reading from that array, which is that file in memory. This is kind of just the implementation of the stream. You implement a function called read, and you basically push it onto the buffer. So this bit here, you're basically saying to the streams that give us more data, continue. So we're going to keep pushing till we've pushed all of the data in that array. So we're basically emulating a fs.read stream, but without actually touching any I/O. So we're going to do the same for write stream. The write stream is not going to write it anywhere, so it's kind of going to be a no-op, but it's still going to be calling these functions. So again, we're not testing kind of how it writes somewhere, we're just kind of testing the internals of streams itself, because it does some really interesting things, which we're going to in a bit. And then we're just going to ignore this here, this doesn't exist. And we're going to do a transform stream. Now this transform stream is our duplex stream, which basically takes input, does stuff to the input, puts it to the output, and a flush is basically, after it's all done that, it does another thing. But we're not going to use that here. And then we kind of wire it all together. So take your read stream, pipe it into your transform stream, pipe it into your write stream, and then when you're finished, call the callback. So let's go back. Cool. So yeah, we benchmark everything together, and this kind of give us some code that we can actually start to benchmark. So how do you benchmark that without having to benchmark kind of the bootstrap of the application? So one way of doing that is by listening on a process exit code inside of Node. So in this case, process.on SIGINT, and then you can kind of do stuff when you get that exit, you get that kill signal to your process. So as you can see, I haven't got it in this one actually, but basically you can kind of trigger your stuff to happen at the point where you want it to. So what does that mean? This means that we can kind of start our application. Application will bootstrap. So in this case, let's oops. So we can kind of start our... Oh, no. Okay, fine. Anyway, it doesn't matter. We're going to start our application, and it's going to start up Bootstrap, but not actually do anything. So we're going to then attach Linux perf. So Linux perf is a tool which is available in the Linux kernel, and it kind of like samples your application n number of times per second, and then prints like stack information about your application. So it can go real deep into the internal application. And we're going to do the first thing, which is basically attaching to a PID. And then when that's attached, everything's bootstrapped. We're going to then fire a kill signal, which is kind of like by typing kill whatever to your process ID. And that's going to kick off our actual reading from our streams. So stuff's going to be reading from memory, processing internally, doing our transform stream, and then writing to our write stream, which is a no-op. So we're going to record all that, and when that's done, we're going to then, that's going to close down, perf's going to close down, and we'll have kind of like all of our data. So that data we need to get out of perf, so we use this second thing here, which is perf script, take it out into an intermediate form, and that's kind of like a flat file output, which doesn't really mean much to us as humans, but it's good for computers, which is good for us in a way. Because then we can use things like this, stackviz, which basically gives us a flame graph representation of our code. So that will basically show us kind of the stack trace in kind of a nice graph, and I'll show you that in a second. So we kind of generate that from the output, create a nice little HTML file, and render it using D3. And then hopefully I can flame graph 1 HTML, if this doesn't crash my computer. And then this will create something like this with large text. What this is, as you can kind of see here, hopefully you can read this here, this is kind of like running Node, so this is kind of the main module of the application starting, and then other stuff happening. So the more and more functions you call, the higher the stack will go, and the stack tree goes up. This one doesn't really tell you much, because it's kind of... Sometimes it's not... they can help you debugging simple applications sometimes, but sometimes you get stuff like this, and it's just like, where's the slow bit of code in here? So there's no way you're going to find out. So you can kind of do a second thing, which is kind of, ooh, that's for later. Okay, back. So you can kind of either use flame graphs for kind of understanding your code path, or sometimes it's better off to actually just do benchmarking of different ideas. Now, after analysing these flame graphs from that application, I managed to find out that inside of streams itself, I might have a second flame graph here. Flame graph 2. This is the better one. Okay, scroll down. There we go. Okay, so this is another flame graph, which is kind of another cool stack, and this is the same application now, kind of with a lot of stuff trimmed out. And as you can see, there's lots of stuff happening. One of the things that, after analysing it for ages, is this thing, which is, there's a lot of these array.built-in array shifts happening. So that's kind of internally. something's calling array.shift, so just the array function, sorting all of the values in a certain way, and that's taken a lot of time. Why? Because arrays in JavaScript or in V8 itself are kind of linked lists, so each time you reorder the array, you're having to rebuild the tree. It's an expensive operation. So apparently every time we do a readable read stream, we're doing a load of time in array shifts. Now, the width of this is kind of how long-ish it's been in that state. So you can see there's one there, there's one there, there's one here, there's one here. So that's going to add up to like 10, 15% of our whole application's time. And that's something that we can start looking into. So the next thing is, basically in this flame graph, it also tells you where that's happening, or it usually does. Basically, I know it's happening in a place called fromList, and that's a function inside of underscore stream readable in Node Core. So let's look at Node Core. So Node Core. So this is the function inside of Node Core. So this is a large function, like we're on line 820 here. And this is, if we scroll up, you can see that there's stuff about streams, and this is where you're declaring the protocol, the prototype on the readable streams, and you've got other stuff here, like resume, add a listener. All these kind of things are probably the primitives you are familiar with streams. But an internal function is this fromList function here. And this is used in this function, which is when stuff happens a lot of time when we read stuff, right? So how can we make this faster? And that's something like I kept thinking to myself. It's like this shift is happening so much. There's got to be a better way, a nicer algorithm to kind of make this whole thing faster. So before I did that though, I needed to kind of test or benchmark this piece of code itself to actually figure out how many operations per second it can do before I can start making changes and seeing if I can make an improvement. So the next thing is, we've already gone through that, is to basically benchmark it. So let's close this, and we're basically going to show the same file again. And this time we've got kind of this bench function here. This bench function just calls our function, which in this case is our fromArray, which is declared at the top. From list there. And then we're basically going to call it a lot of times, kind of get all of the amount of times we call it, measure the time, and then draw a nice little pretty graph. And what that's going to give us is, not that one, a virtualize. Okay, this one, there we go. So this is kind of like the operations it does. So each individual dot is kind of, on each run, how many nanoseconds it took for the operation to complete. Now, we want to make it faster. So now we can kind of like think of another algorithm. So if we think of our kind of array again, where we're taking stuff off the beginning, having to rewrite the tree and put it on the end. What happens if we do it around the other way? If we take it off the end, there's only one. There's no other thing we need to tell to improve its optimization. So let's kind of use pop instead of shift. So pop. Pop. So we're going to use pop to now benchmark this. So we're going to re-implement it again. So that fromList function using pop instead. So here this time we got fromList pop, and we basically have changed the actual function itself to use pops instead of shifts. So you can see here there's a pop, which is great. But we then run this through our benchmark again, and this time, you probably already know what's going to happen, is it's faster. And you can see it's 100,000 nanoseconds versus 210,000 or 220,000 nanoseconds average. So we've actually increased the whole performance of streams. We've made streams that much faster. Or have we? That's the question. So, that's our image. So, yes, it has made it faster, this one function faster. But if you think about it, how streams work is that you've got data coming in and you've got data coming out. So although we're increasing this function by using shifts instead of pops, another function previously will have to do the inverse of that. So it would be doing pops instead of shifts, which means that you're now just putting the performance constraints on the other side of the algorithm, not this single function. So you're actually making streams overall not faster, just this one little function. So benchmarking small functions can be really interesting, but you've got to think about the big picture as well. You've also got the second thing, is that graphs can be deceiving. This is the same graph on the same piece of data. I mean, you can still see there's a difference, but it's now being drawn on the y-axis with a logarithmic scale. So the gap is really, really small, but you can see that this is 1 in 10 nanoseconds, and that's 1 to 10,000 nanoseconds, and you've got 100,000 to 20,000, 200,000 up there. So graphs can be deceiving as well. So the way that people present data to you doesn't necessarily tell the whole story. You have to kind of do more analysis in that as well. Flame graphs, they're a tool in our toolbox. It helped us find this problem, but it doesn't help you fix the problem. It's kind of a thing that you can use to kind of make things better. Sometimes. You just have to use your head sometimes as well. So, thank you. I'm also doing, with some friends and colleagues, a performance workshop at NodeConf Barcelona. So that's NodeConf Barcelona, a little ticket, and we're doing a 15% discount on the regular conference and the workshop. A little bit about NodeConf Barcelona. It's Barcelona edition of the longest running community-driven conference for the Node community. After last year's very successful We Node conference, they are back and they have NodeConf Barcelona. 12 great talks from speakers all around the world. Topics on DevOps, performance, tuning, robotics, and some other interesting use cases. It's on Saturday the 21st of November, and on the following day, myself, Igor, and Hassi, so Hassi's at the back, from Yield, we're going to be hosting a workshop on node performance. So if you'd like to come, this is the link you can use. I'm going to put this in the Gitter chat room as well, so feel free to kind of like use that, and that'll get you 15% off the regular conference, or the regular conference plus the workshop. So this is one-team stream, whitewater streams, fast streams. Hopefully you've enjoyed it. Again, this is our Twitter handles. So thank you very much. Questions? Alan? Hello.
What did you do between the first flame graph and the second flame graph to make it more obvious what was going on?
So how did I clarify what was going on in the first flame graph? So one of the things was kind of making sure I only started profiling flame graph when I actually wanted to know what was going on. So from like user input, I was like, right, I'm going to send a load of requests at this point. The rest I don't really care about. Second, being like an isolated environment. Tertiary thing, basically strip out all of the functions and all of the code paths in your code, which you don't need to know about. Kind of to make it the most simplest test case, which still exhibits the problem. And all of those kind of things, plus like manual deleting things, makes it nicer to see. So, anyone else? If you'd like to speak to me afterwards. Oh, yep. Ben? Hi.
If you're building this in a Docker container,
yes.
Does it change what you do?
If I was doing it in a Docker container, what difference would there be? So, there could be a whole talk in itself. In essence, not really much difference, because you can expose Linux perf tools to the container in a privileged container, so you can do that. You have to do some trickery, but I think I've got some slides somewhere that does that already. If you're doing it on boot to Docker on your Mac, you're going to have some big problems because they have a custom kernel, so you have to recompile the kernel yourself, add in the kernel sources for Linux perf, and then recompile the kernel yourself and use that boot to Docker image if you wanted to. But that's kind of a special edge case. But it's exactly the same, pretty much, just in the privileged container. Anyone else? Thank you.